Hi there. Let's look at what's the matter. Matter is actually something fills up the space and it has a mass. Good example is water. So the water exists in three states of matter: solid, gas, and liquid, right? So we're gonna look at in a water molecule. If you just break down one small drop of water into very smaller and smaller and smaller, so you keep breaking into very small units of water droplets, and you're going to finally theoretically going to end up with the smallest portion of the water would look like this one. It's a water molecule. So the water molecule has two hydrogens and an oxygen atom. We already know that. So two atoms of hydrogen and one atom of oxygen. Now, so we can call these ones are molecules, right? So the molecules are also kind of compounds. Now, if I add a bit of sodium chloride into this water, it would make a mixture. So we can talk about mixtures separately. Now we are clear about the compounds or molecules. Now let's look at this one. The hydrogen atom itself should look like this. So the hydrogen atom has a proton which is positively charged, and it's in the nucleus, and it has one electron floating around in this, orbiting around in this circle. That's the electron. This is the proton, right? Now you have a plus and a minus, so it's electrically neutral. The atom is electrically neutral. So that's that. So now the atom is in an element, one unit, the smallest unit is an atom, right? Now atom also neutral, we should call it electrically neutral, because plus and minus cancels out, right? Okay, now how do we write this on H1 and 1, right? So that means actually one proton and mass is 1. Now here helium is the next one. It has two positives, two protons, and two electrons, so to cancel out. So two pluses and two minuses give you zero charge, and it's a neutral atom. So not only that, in helium there is two neutrons, so the mass is total of 4 together. So the two blue ones and two red ones, right? Two neutrons and two protons. So the total mass of this atom is 4 atomic mass units. That's what it is, right? Now, I did not talk about the mass of the electrons. It's almost negligible for now, right? Okay, so the two electrons are almost, we can consider there is no mass. It's actually 1 to 2,000 roughly for considering to a proton. Now these electrons are existing in, we call the shells or energy levels. That's also in the periodic table. It's the period. Now let's look at this one. This has 6 protons, so that means atomic number is 6, and that has to be carbon if you look at the periodic table, right? So 6 pluses in the nucleus, and there's 6 neutrons in the nucleus. So the nucleus is pretty heavy, and it's 12 atomic mass units, right? Now we also have 6 electrons, right? Because there's 6 pluses, and to cancel out we should have 6 electrons. Now these 6 electrons exist here. So 2 electrons in the inner circle, we call it core, and let's put it in a lighter green. So they're kind of different. The core electrons also we call the shield electrons, because it shields the nucleus. And the outer ones, I put it in a darker green. So those 4 we call the outermost electrons or valence electrons. So they are responsible for chemical reactions, so they're very important. So valence electrons also shows what is the group in the periodic table. So it's really an important thing when you look at the patterns of the periodic table. So the outermost, the valence, If it is 4, it's fourth group. If it is 2, it's second group, and so on. All right, let's put the label here. The inner ones are chemically not very important, but they are co-electrons. They are not taking part in reactions, and they are also called the shield electrons, right? Okay. Now we can look at, we looked at hydrogen, helium, and carbon. Carbon should be written as carbon 612. Helium should be written as helium 2 protons, and 2 plus 2 protons and neutrons 4. And hydrogen should be 1 and 1. So hydrogen is 1 and 1, helium is 2 and 4, carbon is 6 and 12. So that's, now there are 118 something elements there, so it's going to be difficult to understand. So let's look at a pattern. This is the pattern. So any element would have a symbol, and it would have a number of protons, the cage of the periodic table, and it would have a mass number, which is capital A, protons and neutrons, right? Okay, now, so again, if it is hydrogen, we should write it like H1 and 1, right? If it is helium, we would write HE 2 and 4, right? And if it is the 4 comes from 2 neutrons and 2 protons, right? And the 2 is the protons, which is the atomic number, the Z, and that gives the cage. Carbon is 612, so that's it. Now there are isotopes, and we can talk about that in a different video. So we want to do some calculations and understand what's the abundance of isotopes. That's the same different atoms in the same element, right? Now let's look at the periodic table. Now rather than learning hydrogen, helium, neon, all these things, it's better to look at the periodic table as a whole, right? So 118 plus different elements, we can look at patterns here. That's the important thing, looking at it. So the periodic table is built upon a number of protons, Z, the atomic number. So it goes hydrogen to helium, and so on. So, and also there are top to bottom groups. These are families, and families have similar characteristics, and the families and all the groups in the periodic table also have the similar characteristics, right? They're in the same family, kind of like little brother, big brother, and sort of thing, right? They look the same, right? Similar. Okay, the other thing, there's rows, horizontal, we call the periods. These are going from left to the right. So the left to the right periods are actually periodically changing its properties. If you look at lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, they change nicely back to sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, likewise. And right, so that's the columns and periods. That's not the only one. See, look at this little ladder, the light blue ladder. And that one separates this little box of a periodic table into two sides. This upper right corner is called non-metals, right? Non-metals are mostly gases and liquids, and the lower left corner is called the metals. So these are clearly different from each other. So we can put it into different tables, so it's kind of easy for us to see. So we can look at few properties and metals and non-metals. So what's the difference, right? Yes. Now in this case, what we can do, so let's take a little bit of space for between the two things, metals and non-metals, right? And the states of each is metals are hard solids and non-metals are liquids and gases, right? And if they are hard solids, and they will also have the quality, different qualities, right? So what they are, they should look they are malleable. Malleable means you can hammer that to different shapes, and if you can make pipes and tubes, we call it ductile, right? And you can make into plates. We can hammer into plates and wires and whatnot, right? That's called the malleability. That's the nature of metals. Just think any metal, you know, aluminum and iron and gold, silver, all these things. But the non-metals, it should be pushed this way. So the non-metals are brittle and dull. So what's the brittle and dull means? They are, you can sort of make it to a powder, and they are not really shiny, the non-metals, right? Good example is sulfur, right? And luster is just for shiny metals that we use. There are other terms to use, but generally this is good enough for us, right? Now the melting points and boiling points, and these are higher in metals. They could vary from 500 to 2200, something like that. So they're depending on the type of metal, silver, gold, iron, and tungsten, and so on, they're pretty high. Now non-metals should have lower melting points and boiling points, right? Okay. The reactivity is also an important character for metals. So the metals would like to give up electrons or lose electrons, and they would make cations most of the time, right? There are a few exceptions, but they will make cations, which is positive ions, and they will lose electrons, right? And that's the nature of metals. Then non-metals would be the opposite. They will gain electrons and make an anion, right? So the anions are also important. So that's the nature of non-metals, right? So the cations and anions actually come together and make ionic compounds. We will be talking about different compounds later, right? Now, what's the other important thing here? It's good to know here, acid-base nature of these elements. So oxides of metals or metal oxides will make basic compounds. So good example, sodium will make sodium hydroxide, and aluminum will make aluminum hydroxide, right? Like antacid fills, right? Okay. So non-metal oxides would make acids. So that's something we want to know. So what's a non-metal oxides? Good example is CO2 will make carbonic acid, and NO3 will make nitric acid, and SO3 will make sulfuric. So these are a few examples. So we can make this one a little bit visible, one side to the other. And so now these are the two extremes in this box. But like I said, the latter shows something a little bit different, right? And those are called metalloids. Now, we got the extremes of non-metals and metals. Now the metalloids are actually in between characters. So their properties, the chemical and physical nature, is actually in between. So the metalloids are in the center here in this case, because I'm sort of ranking the properties, right? So what they are, the boron, right? And silicon and germanium, boron, silicon, and germanium. It stays like a diagonal ladder. And then we also have arsenic and antimony. Arsenic is As, and